Welcome, everyone. We are back with another quick tip. I have some more product team members with us today that I'm going to bring on camera here, and we're going to talk about the native Spark execution engine. I think you're going to love this. This is a great new feature, and everyone should start using it right away and start testing it out in preview. With that, I'd like to bring with me Estera and Ankita from the Microsoft product team. Welcome. Thank you very much for presenting to us today. This information was presented at the Microsoft Fabric Conference in Europe just recently, and the team has been gracious enough to come on the channel and talk more about this incredible feature that we need to really start taking notice of and paying attention to. Estera, you can kick it off for us.
Yeah, thanks for having us. It's a great pleasure to extend our visibility on YouTube and reaching out to not only Spark lovers, data engineering lovers, but also to Power BI lovers with a great enhancement that we recently roll out, which is native execution engine. And today with me like I'm the product manager for that functionality, working as part of the Azure Data Synapse and Fabric product group, focusing on data engineering on Apache Spark. And together with me, Ankita is joining. She's like the best of the best from the engineering team. Together we presented that topic like 3 weeks ago in Stockholm during the FabCon conference, and I'm just happy to share with you the context. What is the functionality about? So just again, straight ahead, let's kick off the talk because I want to share what is the context here. We are going to talk about data engineering, something related to data science, data integration, the feature that is helping all of those three stream area. But the context is that Apache Spark revolutionized big data processing. It has been introduced in 2012 as the replacement of Hadoop's MapReduce. Spark very quickly started to gain the traction. 2016, we got the new companies. Why? Because this is the go-to tool for handling both batch processing and streaming processing, all for big data. And today, the appetite for results, for analysis is even faster. We want the analysis now. And the challenge is that Hadoop's MapReduce was slow. Why? Because the data sits from disk. So we read the data from disk storage. Apache Spark brings the change because we are accessing the data which sits in memory. So because the demand is faster, the need of rapid data processing and stream data processing has never been higher. That's why we have the solution that we are still working on this journey to make the results immediate, give you the immediate gratification, but the reality is that today we can share that we can compute the results faster, just with native execution engine. In short, today we are going to use the word native. So the agenda that we want to share with you, the points that we want to share with you together with Ankita is that, yes, the context of, first of all, what is Apache Spark in Fabric? What we did as an engineering team? Then what's native execution engine? We'll show you the demo. And then Ankita will go through the deep understanding of the execution. So stay with us. And now over to Ankita to share the deep dive directly from the engineering team.
Thank you so much, Estera, for that amazing introduction of the work we do at Microsoft and of me. But I don't know if I can be called the best of the best, but I do my best. So I think to really understand the native execution engine, you sort of need to understand how Apache Spark works in Fabric at the moment. So in Spark, you essentially typically have a cluster with a driver node and one or more executor nodes on which your tasks actually run. So the driver takes input from the user in the form of a SQL query or a data frame API. And this is then parsed and converted into an unresolved logical plan. So this unresolved logical plan goes through a series of analysis and validation to make sure that the tables that you're specifying actually exist and so on. This logical plan is then optimized to what we call an optimized logical plan. And an optimized logical plan is converted or translated into a physical plan one or more physical plans which actually specify how the query is to be executed on the cluster, what specific join algorithms to use, for instance. And through some cost model, we pick one physical plan out of the many physical plans that are generated that the cost model deems to be the most efficient for the given query. And the driver then breaks this selected physical plan down into tasks based on data partitions. These tasks are then transmitted to the executor, where code is JIT compiled, executed, and results are sent back to the driver. So from input to output, this is essentially how a query is executed in Spark. So Spark has been an offering on Azure for a very long time, and in the years that we've supported Spark runtime on Synapse and now on Fabric, we've done a lot to make sure that Spark on Azure is much faster than what you would get on open source. So we've query optimization. The nature of your query, the way it's actually executed on the cluster, depends on the level of optimization of your plan. So the more optimized a plan, the faster it's going to execute on your cluster, the faster you're going to get your results. And we at Microsoft have worked on a ton of query optimization features over the years, all of which have made Fabric Spark multiple times faster than open source. A few years ago, we announced the intelligent cache, which speeds up access to frequently queried data by caching it on your local cluster. And through Delta Lake, we now have optimized storage formats. And specifically in Fabric, we offer a feature called Optimized Write, which aims to make sure that the number of files that are written is smaller to sort of speed up your subsequent reads and other operations on these files, because you have fewer operations to perform on a smaller number of files. So there's something called Amdahl's law, a very famous law, which states that the overall performance improvement gained by a system depends on the fraction of the system that is actually optimized. So you can think of it as stressing that to get bigger bang out of your buck, you gotta focus on some part of your system wherein the investment that you put into optimization can result in overall speed up or just much better optimization on the entire system rather than just its tiny fraction. So we got thinking, what is something we can optimize that will impact the entire chain rather than specific parts of the Spark pipeline. And we went and we tried to figure out what are our opportunities for improvement. So Spark is written in Java. Java was released and offered a platform independent sort of paradigm. So it was a write once, execute anywhere programming paradigm, meaning you could write Java, compile it on any machine, and then run it on any other machine. So this platform independence was great. It meant that you no longer had to worry about, what was your targeted operating system or hardware, but it also meant that you lost out on certain targeted optimization. For example, on C++, there are a lot of compiler level optimizations that you can run for specific hardware. Java was also great because it offered automatic memory management and garbage collection. So this was awesome because it took the burden of looking out for memory leaks away from the developers through its independent and automated garbage collection. But again, this has its own overhead, and your programs can pause for specific cycles related to garbage collection. So could we maybe replace Java with something else that is faster? Second, Spark is a row-based engine, but the most popular data formats that we use, especially for analytics, are Parquet and Delta, which are both columnar. So Spark, being a row-based engine, is probably not making the best use of the way data is stored in disk and then brought into memory. And lastly, hardware. So SIMD is a parallel programming paradigm by which a single instruction can be applied on multiple data points at the same time using special registers in memory. And this just brings about another level of parallelism to your programs. And Spark does not make extensive use of SIMD instructions. Now, most compilers can sort of figure out how to apply SIMD and unroll a tight loop. But in most cases, you need to explicitly use SIMD intrinsics in your code in order for that, that instruction to be executed parallelly on your CPU. So we have these three areas of overhead, and we kind of thought, is there one thing that can attack all three at the same time?
I want to ask a quick question here to you
Yeah.
about this one. So the JVM overhead, well, one, I love Spark, starting off there. It's awesome, but I don't necessarily love writing Java. I'm not a great Java writer. I don't like writing it. And a lot of this is abstracted away from me in notebooks because I can use Spark SQL. I can use Python in there as well. So, I mean, just to be clear here, the JVM engine that's that's part of the Apache Spark open source project. That's kind of like where we kind of originated from, just to be clear too, right?
Yes.
Okay.
Yes.
Excellent.
So I think what you're talking about is like the interface that a user would use with Spark, which is like
Yes.
PySpark or Scala.
Yes.
But the actual engine, which takes
The
in your
lower
queries
level.
and run, yeah, that is written in Java, so that executes on the JVM.
Good. I'm going to make this very clear for our users. For those of you who are coming from the data engineering world, this will be like, yep, we get it. We understand. We know what's happening here. But for me, coming from the Power BI world, there's a little bit of a mental shift we have to think about here is like we're writing, we're not writing code directly against the machine. We don't have to write Java to make this engine work. We're using like abstracted layers of language that we can easily write. And again, we all love SQL. So anywhere where we can put SQL, we have a huge audience of SQL developers that are in the data engineering space, but they can come to this and know, oh, I don't have to write Java. I believe Spark also runs on Scala as its native language as well. Again, we don't have to write that. You can get better performance out of those things. And I think that's where you're going here as well. But I just wanted to point out for us, as the Power BI world is observing this, the tools that we're using or the language we're writing is probably primarily Python and Spark SQL, which is very close to T-SQL as well. But I think this is going to also start shifting and changing as we're improving the engine here as well.
Yes.
Awesome.
And it's interesting that you spoke about, PySpark and Scala, but this is actually one of the things that made Spark a lot more popular than
Yes.
Hadoop because it offered super user-friendly APIs in so many different languages.
Oh, 100%.
Yeah.
Yes, I had in my data science days, I had to build my own Hadoop server and run what it was. What's the in-memory engine on when they came out with originally? It wasn't Spark originally. What was there's some other Hive or something. Anyways, turning all that stuff on was a pain, and I did not like doing it. So the fact that all this has been abstracted away from me, the user, I can literally drop in, hit a notebook, start writing Python, and things just start working.
Yeah.
This business users take note. This is the power of what we're talking about here. This engine is incredible, and all of that's being made easier for us to interact with it. So I just want to bring out that point and ask the question and clarify a little bit there. So sorry, I didn't mean to interrupt. I'll let you get back to it.
No. Yeah. So there's this. Okay, I'm going to say it's a myth. Everybody says C++ is the fastest language out there. It's way more fast than Java, but this is not just anecdotal. This is based on real world benchmarks. So I have this little table up on the screen, which I've taken from a paper written by Robert Hunt out of Google. This is quite old. I think the paper is from around 2011 or 12. But what he did was to come up with a very well specified benchmark that did not use language specific features or optimizations that would put one language ahead of another. So with this well specified benchmark that didn't take advantage of anything specific from the language, he found that C++ was the fastest language out there. And if you look at the performance of Java and Scala as a factor of the execution time in C++, C++ is 1x, Java is 5.8x slower, and Scala is 3.6x slower. And the other screenshot that you see on the slide just shows what you would typically see in your Spark history server when you execute a query. If you're curious enough to go and see, how exactly that query is being executed, you will always see that after you scan Parquet, there is a columnar to row, meaning your data is in columnar format, but it's being read and then converted into row format so that Spark, which is a row-based engine, can actually execute on it. So what's all this fuss, with SIMD and columnar data? So columnar storage is great for SIMD because it ensures that your data is well packed into these dense arrays that can then be easily transferred from memory into these SIMD registers. So if you have a very simple query where you're just summing up two columns, in row-based execution, you would have to execute it one at a time. So, A0 and B0 gets added and the result emitted A1, B1, A2, B2, A3, B3, A4, B4, A5, B5. So, if there was a way to parallelize this, that would be great. And that is exactly what happens when you have columnar with SIMD. The entire set of data is loaded into SIMD registers at once, and the data is, your result is emitted in one go. So this brings about another level of parallelism, and the degree of parallelism just depends on the size of your SIMD registers. So if you're summing up, say, like 8 bytes and you have 128 bytes of SIMD memory, then you would be able to do 128 by 8 in parallel. So fast is never fast enough. So this graph is taken from the International Data Committee. Just shows the rate at which data emitted is growing. So with exploding workloads and the exact same software and hardware stack, we are challenged to provide faster analytics so that with your existing budgets, you can do more with the same. And so with everything that we've laid up so far, the couple of pitfalls in Spark, but there are actually areas of potential areas of improvement. And the tons of things that are being left on the table, for example, JVM overheads, SIMD registers, all of which are just available on the regular hardware SKUs that you have in clusters. We have our solution in the form of the native execution engine on Fabric.
I want to pause just really quick on that slide. As I know you moved ahead real quick, I just want to make a real point here. For those of you who like data and maths and things, this is looking very exponential in nature if you look at this data here. So one observation I see a lot on the podcast that we do is we have to recognize that the amount of devices connecting to the internet, the amount of video content that's being created, everything we're doing is going to consume and build more information. So we're seeing this ever-growing rate of data. And so we have to stop thinking about how we've been doing data things in the past, because those tools just will not work for the increased volume that we're moving towards. So I love this graph. This is so indicative, I think, of where we're going. And one of the main reasons and importance here why I think this team is doing such a great job is this is an engine that can really help us move towards these larger data volumes as we continue to grow. So excellent work. This is a great slide. Love this.
Yeah, and Apache Spark, again, aim to do the big data processing. We as a team focus on big data processing. I'm emphasizing the big, right? The high volume. At the same time, we understand that out-of-the-box open source technology needs tweaking, needs optimization. So again, after understanding pros and cons or limitations of Apache Spark, we want to show you the native execution engine. Again, the best way to show you what is that, how to enable, how it works, is just to see it in action. So let's watch the demo. Please, unmute the.
We're excited to announce that the native execution engine now supports runtime 1.3. The native execution engine's core consists of Velox, a C++ database acceleration library, and Apache Gluten, which offloads JVM-based SQL engines to native engines. Let's dive into a demo. We have a notebook scheduled to run daily at 5 a.m. This notebook runs 5 complex queries, performing data transformations and heavy computations typical for business analytics scenarios. Specifically, it analyzes weekly sales data by day of the week for different stores over specific time periods. I'm using runtime 1.3, the latest version, which has recently transitioned to general availability, GA. Recent updates include upgrading Delta to version 3.2 and enhancing the Python ecosystem. This runtime is now ready for production workloads. Let's run the scenario with default settings, without the native execution engine or any performance optimization. Currently, this notebook takes about 670 seconds, or around 11 minutes, to execute each day. Now, let's optimize the execution. The simplest way is to enable the native execution engine. We'll create a separate environment named Optimized Environment. I'll navigate to the Environment tab, find the Acceleration section, and enable the acceleration feature. You can activate the native execution engine at either the environment level or for individual notebooks or jobs. Enabling it in the environment settings means all associated jobs and notebooks will automatically inherit this configuration. The Acceleration tab makes enabling the native execution engine seamless and straightforward. Now, back to our scenario. I need to switch the runtime executing my notebook from the default one to our newly created and optimized environment. Let's run the notebook with our scenario without making any changes. While the queries are running, it's important to note that the native execution engine is fully compatible with Apache Spark APIs. You can use Spark SQL API with PySpark, Scala, R, and Spark SQL without altering your code. Simply activate it and continue as usual. And voila, the results are in. What used to take 11 minutes now completes in just 112 seconds, less than 2 minutes. That's a 6 times speed improvement for this scenario. The performance gains are evident. The current release of the native execution engine excels in scenarios such as working with data in Parquet and Delta formats, handling queries with complex transformations and aggregations, and running computationally intensive queries. We encourage you to enable the native execution engine on your workloads at no additional cost. You'll benefit from faster job execution without paying more. Effectively, you pay less for the same work.
Bringing you back in here, one demo was amazing, love it. The thing that people don't get here is same performance, better performance, 6 times speeder, faster performance. I'm literally stuttering over my words. I'm so excited about this. It's so much faster, and you're not getting charged extra. There are other tools in the ecosystem that charge you more for optimizations like this. You're just getting this out of the box. I can't stress how important enough this is from us, the development, the community, the tool. This is a huge move, and I'm very, very excited to say I'm just thrilled about this announcement here.
Yeah, we believe it's a game changer. We have been working on that for the recent years, and lots of months spent on testing as well. But as you've seen, I want to emphasize, first of all, the newest runtime. So all of the users, please change the runtime version on the workspace level from 1.1 or 2 to 1.3. 1.3 is the fastest. The new version of runtime is usually faster than the previous one. New generation, more functionalities. So first of all. Secondly, enabling native execution engine is just a checkbox. No matter Spark SQL, R, whatever the language, just a checkbox that right now you can enable on the environment level. And then, of course, we see so many different use cases. You process so many different data types, data formats, and then data types. Again, this example, those are real queries. I'm happy to share this notebook. You can test on your own, but the reality is that the performance boost is different from case to case. So what we are doing in the backend. So we run extensive benchmark almost every day, including 2 standardized industry benchmarks, TPCDS, TPCH. And here on the slide, you can see that we are comparing default Fabric Spark versus Fabric Spark with native execution engine enabled. And here what we see is that if you enable native engine, by default, your job's execution is twice as fast. So for example, if your job takes an hour, with native engine, it will take half an hour. Of course, everything matters what are the queries inside. But the queries you've seen on the demo, I'm happy to share it. Those are real examples. So benchmarks, this is one aspect, but the reality is what results you are getting, so customer workloads. And here we have an extensive telemetry. We are just checking and comparing based on what we can access to and what we can see. Based on the results also which are coming from our partners and customers, we've seen on average from 2 to 6x performance boost. The boost is, for some queries, it's even faster, but everything depends what is the query about. So it differs per query and per scenario. Now, I'm open for question, or we can go into the what's inside. So how the native execution engine is built, what are the building blocks, what are the two hearts, and what the team has been focusing on, and also how the execution look like. So the deep details for the every data engineer.
Let me just ask you one question. The chat's been very excited here. Some people were asking things about Spark and looking at the back end. And this is this is from the business user world. We're coming from SQL, that world of things. This is kind of a bit new for us. The execution plan, looking at all the different steps that are happening. This is a new world for us to kind of look at, which is not bad. But my question here really is, there are, to be very clear, your workload is unique to what you built in your notebook, whatever that code you're running is. And what we have found is as well, very much similar here. The more you work on that code, you can make your notebook code, you can change the code in the notebook, or you can change the engine, or you can change a compute itself. So I can bring more compute to the cluster behind the scenes, or I can bring more memory to the machine. All these things can kind of impact the runtime of jobs. So I'm really pleased to see this one. And if you guys had to kind of just really quickly summarize, what are the main workloads? I think you said it there in the end of the presentation, but maybe just summarize those two or three workloads that I should be focusing on that does see some substantial improvement. Working with Delta, Parquet, and then there was a couple other ones, so the transformation sides of things.
Yes. So first of all, Delta, meaning that you process the data coming from Delta Lake, so from the lake house, or from in the Parquet format. This is the first one. And this is the main qualifier, kind of a main qualifier. And secondly, native aims to process big data. So if you have a query that takes just a few seconds, 1, 2, 3, sometimes like you write those queries, very, very simple one, then the boost of native can be, small, because what we focus on is a big data processing, so big workloads.
Sure.
If there is a query that takes you half an hour, and we have a few customers I was working with, they were struggling that they have a query that takes 3 hours every night because they are processing, right?
Yes.
And, tons of new data coming. Then this is the perfect scenario. So intensive queries. So if let's assume that the baseline is the medallion architecture.
Yes.
So bronze layer is when you land the data, raw data. So here, the impact of native execution engine is minimal, because what is happening? We are just writing the data. We'll focus and optimize writing within the upcoming releases. Like in the future, I would anticipate that within 3 to 6 months, we should optimize that as well. But as of today, as of 18th of October, we focus on the second layer and the third layer. It means that if you process from bronze to silver, you do transformations, aggregation, sorting, processing. This magic is optimized by native. And then, of course, the last layer that is happening between silver and to gold. So processing the data, as you could see, the notebook with tons of queries, tons of different joins. Here, the team has been spending so much time on optimizing the joins, the way how you can bring all your tables across all the workspaces or the lake houses, and then get the insights.
Awesome. Thank you for summarizing those, because this is the points that, as we're new looking at this thing, it's I really like you emphasize that, and it's bigger data, jobs that take a long time. So if you're looking to implement or test these things on your workloads, find the jobs that are running a bit longer. That's a good candidate for us to test this out too.
Yeah, and small detail you mentioned about, there are different ways of optimizing your job execution, right?
Yes.
Because you can increase, yes, of course, you can increase the machine, have more executors, more memory per each. Of course, yeah, you need to do the tweak. And the reality is that, okay, you increase and you have to do some empirical checking, do the maths,
Yes.
okay, because the higher machine, the more you are paying, the more consumption is going from your CU, right? So it is one optimization. Lots of manual work. The second optimization you mentioned, which is about tweaking the code, because writing an optimal code is an art. We have Copilot, but this is still an art.
Yes.
But this is optimization.
Yes.
And there is one more optimization that is adjusting lots of Spark settings. Spark has around 400, Delta has around 200 different settings that we can optimize to make the execution faster. But here, 2 details. One is that expertise, and this is the art as well. And secondly, you do that query by query. because every query is different. And sometimes you do a join, which is broadcasted across your executor. Sometimes it's not, because it's a different type of join. And the reality is, lots of resources, lots of time spent on optimizing that. And what we did here is just by enhancing the engine of Apache Spark engine, by adding a plugin which is native execution engine that is accelerating that, and no optimization. Of course, you can add your optimization on top of that, but the default, that the results you can see on the screen, is happening just by enabling that. No more configuration, no more tests or checking. You can do that, but it's not needed. It's optional. By default, what we want to deliver in Fabric is the default experience, default optimization that works out of the box. And there are cases that sometimes you would like to even do the next step. You can do that. But
I love it.
With native engine, it's just a simple checkbox.
I get so excited. You're just making it easier for me to sell this thing all the time. I love it. This is super exciting. All right, excellent. Let's go into, if you have some more slides, we're free.
Yes,
no more questions from my side. Feel free to go deeper now. Let's go a little bit more deeper with the engine.
Over to Ankita.
Okay, so let's jump in and figure like, what is the native engine? Where is all this boost coming from? Like, what exactly is it doing? So aligned with Microsoft's commitment to open source, the native execution engine is comprised of two open source components, Velox and Gluten. Estera, next slide, please. Thank you. So Velox is an open source project out of Meta that is now developed in collaboration with a number of companies, including us at Microsoft. Velox is essentially a C++ database acceleration library, which is intended to accelerate your compute-intensive operations. So it's a single node library, which means that it does not have the scaling power of Spark and cannot do so without an orchestrator at the top. Velox also does not have a parser, and it has no global optimizer. So you can't directly interface with it, but it's rather meant to be integrated into some kind of data computational system. And all Velox does is it executes the plan given to it, and it executes it fast. So Mike, earlier you were talking about how you can make workloads run faster by throwing more compute at it or throwing more machines at it, right?
Yes.
So let's say you did throw more machines at your Spark job, but then you come down to one task, just one task, which cannot be distributed across many machines because it's a single task, and that one task is slow. So to make your workload faster, you need to make that one task run faster.
Yeah.
And that's what Velox does. So
Awesome.
without throwing more resources at it, it just
Yes.
accelerates the execution of these individual instructions so that overall your job is just super fast.
That's killer. I can't underestimate how great this is, because again, we're new to this. If we're coming from the BI world of this, I don't know exactly what knobs to turn yet. And over time, the community will start learning more about this. People will figure things out. We'll read more blogs. It'll get better. But the fact that you're giving this out of the box and you're already working hard to make this easy, less knobs for me to have to adjust to get good performance, that's the power of this. This is why I'm so excited about this feature.
Yeah. So like I said, Velox is a single node library, which means it cannot scale out by itself. So Velox needs something to integrate it with Spark, which actually has like the true scale out ability. So Gluten is a project that was originally created at Intel and is now part of the Apache incubator. So it is literally Latin for glue, and it acts as the glue between Spark and Velox. So you can think of it as Gluten is this middle layer that kind of orchestrates this dance between the scale out abilities of Spark and the raw execution power of Velox. So what Gluten does is it takes in input from the user, it takes in instructions from Spark, and it offloads this execution to Velox. So it does this by defining a Java native interface, which is a way for Spark, which is written in Java, to talk to Velox, which is written in C++. So given Spark's plan, like the plan which specifies how exactly a particular query or like a data frame operation needs to be executed, it takes this as input, transforms it to something that Velox can understand, and it also handles the transfer of data between the C++ library and Spark, and it does this all using the Arrow format, which again is another open source project. And why Arrow? Arrow is really great because it makes sure that data is well aligned in memory and so can easily leverage SIMD instructions. So we have Velox, we have Gluten. Both of these make up the native execution engine. So where is the boost coming from? So Spark is written in Scala, which is executed in the JVM, and we spoke about this and how JVM comes with its own overheads. The native execution engine, of which Velox is the execution component, is written in C++. So that means it is executed natively, not in any kind of virtual machine. Scala and Java programs are compiled just in time. That means at runtime, they're compiled and then executed. But C++ libraries are compiled ahead of time. So this means that while you compile, you can do a bunch of things to make sure that your resultant binary is highly optimized for the targeted hardware or selected hot paths. So Spark, again, which is written in Scala, also has automated garbage collection. This is great because it means developers don't really need to worry about, memory leaks or the like. But the native execution engine is written in C++. This offers fine-grained memory control. And this means that the developers of Velox have the option to do a bunch of things with the available memory that they have. For example, Velox does certain things like it reuses buffers during execution, or if you have to perform certain string operations, it can do all of this in place without allocating new memory and rewrite it, etc. Spark is a row-based engine. This did not utilize the fact that input data in Parquet and Delta is already in columnar format. The native execution engine, on the other hand, is column-based, which means it takes in input in the form of column batches and executes on these column batches without needing to convert from columnar to row. Spark did not extensively use SIMD instructions, and the native execution engine explicitly has SIMD intrinsics littered throughout the code, which you can actually go ahead and explore if you go to the Velox GitHub page, look at the code, you will see the usage of SIMD, AutoSIMD in a ton of places in several operations all throughout execution. So I'm revisiting this little architecture diagram from a few slides before to understand where exactly the native execution engine really fits in with Spark. So once you have the physical plan, Gluten is sort of written in a way that it reuses as much of Spark's control flow as possible. So the goal of the Gluten project is to not like disrupt too much of Spark's flow, but to kind of squeeze in at a point where a lot of the work is already done. So Gluten takes in a physical plan, applies a bunch of transformation rules, which essentially tries to say where exactly can I execute some operation in the plan in native. And instead of having regular tasks which are executed in Java, you now have these native tasks which are sent down to Velox, executed in the Velox library. And all of this, the data transfers, the instructions, all of this happen through the Java native interface. So let's go like just one level deeper. The native execution engine is implemented as a plugin. So a plugin is something that Spark has, which just allows you to sort of extend the features of Spark without needing to massively overwrite or change or break any existing scenarios. So Gluten is implemented as a plugin in Spark. So once you have the physical plan, Gluten takes in this physical plan, it runs a bunch of transformational rules on it, to convert it into a plan that Velox can understand. Gluten also has a shim layer. So this allows us to support and develop multiple versions of Spark at the same time. So at present, we do support runtime 1.2 and 1.3, although as Estera mentioned, 1.3 is our preferred runtime. So the native execution engine, Gluten and Velox, these are a work in progress. There are a few operations, a few functions here and there that are not supported. So this does not mean that if your Spark job has a function or something that's unsupported, that the application will fail. Instead, Gluten has the ability to kind of seamlessly figure out what can be executed in native, what needs to fall back in Spark, and accordingly transform the plan into something where certain operations can be executed in native, certain operations can be executed in Spark, and overall your job succeeds seamlessly without you knowing what has been executed where, except that it will be accelerated. And the Gluten plugin on the driver also collects metrics from from the native library, which executes the actual instructions. And all of these metrics are reported in your Spark history server, just as they would with regular Spark. So you can actually go in, see, how long your join took, what operation in your join took the most amount of time, how many rows were emitted, how many rows were read, etc., etc. So once you have this transformed plan on the driver, this is then broken down into tasks, converted to a plan that a native operator chain that Velox understands. And these tasks are then executed in the Velox engine, all in columnar batches, and the results are sent back to the driver. So, two important classes run on the executor. One is a columnar shuffle manager. So a shuffle is essentially this process by which data is redistributed across executors in a cluster. So you need to shuffle when you have, for example, an order by, essentially something where data needs to be shuffled across to make sure that all values of a particular type are located on one particular machine. So shuffle is column based, which means you don't need to go back and forth between row and column. And second is a memory manager. So this is a very important part of the native execution engine, which really makes it a seamless experience for users. So we'll dive a little deeper into this in an upcoming slide. But yeah, I just want to highlight that this is a particularly a very hidden feature, but something that's crucial for user experience for anybody who's using the native execution engine on Fabric.
I want to make a point here. That is the best diagram that I have ever seen around ripping out all the different things that are happening here. And I think this was actually quite funny for some reason, because when I talk to my family about what I work on during the day, I'm like, oh, I'm doing this and I'm running on Spark. And they're like, Spark? Like electricity? No, it's different. And now we have all these fun new terms that we're going to have to learn, like gluten, Velox, shim layer now. Like these are fun terms, but it's good to start learning the lingo, the language of how this engine works. Again, at the end of the day, I'm in a notebook, I'm writing SQL, I'm writing Python. A lot of this stuff is just happening behind the scenes. So I just want to be very clear. This is really cool. A lot is happening and making this incredibly efficient for us when we can get to these hyper data scale things. Very great slide. Just want to point this out. Very awesome diagram here.
Thank you.
And the purpose that, of this talk, of this evangelization, is that we want you to know the details in the backend, because yes, this is a checkbox.
Yes, exactly. It's blowing my mind. You're literally doing one little thing here, and all this stuff is just happening automatically. So I'm guaranteeing you this has been a lot of thought and a lot of work from the team to really make this a reality. So excellent job, team. Keep up the good work. Sorry, I didn't mean to interrupt there, but keep going. This is great.
So coming to the native execution on Fabric and how you can use it. We do support runtime 1.2, which is Spark 3.4, and runtime 1.3, which is Spark 3.5, although we recommend that you use runtime 1.3 because, we plan to deprecate active support for 1.2. Like Estera has been saying, the native execution engine is just one switch. It's one-click enablement. You need absolutely no code changes to your existing notebooks or Spark job definitions. Enable one click and your workload is accelerated. So Gluten and Velox are open source components. So they're literally available for you to download, compile, mess around with. But this does not necessarily mean that you will be able to upload these as jars by yourself on Fabric. There's a lot of work that we've actually done to make sure that its integration into Fabric is seamless and that it works with Lakehouse and all of the cool features that Fabric provides. So one lake integration, we have integrated Velox and Gluten with one lake. This means that you can read data from your files and from your tables. It is integrated with role-based access and Entra ID authentication. So all of your existing permissions will be applied as is, and you will be able to read from lakehouses in your workspace. Delta support. So Delta is sort of the champion of Fabric. It's the preferred table format. And Delta wasn't the most well-supported feature or rather well-supported scenario on Gluten and Velox when we first decided to adopt this as for our use in Fabric. And the Delta team in Microsoft did a lot of work to ensure that existing scenarios in Spark using Delta were seamlessly supported on the native engine, whether they fall back to Spark or whether they are executed natively. Dynamic memory management, like I said, that memory management is a very tricky area, especially when you have to handle Java memory and C++ memory. So we developed a dynamic memory manager, which makes all of this just run seamlessly in the background so that you just have one switch enablement. Fabric has this cool feature of starter pools where you don't really need to wait for a Spark session to initialize. When you enable the native execution engine, you do not lose this cool feature. We have the intelligent cache, which speeds up access to your frequently queried data. The native engine is integrated with intelligent cache, which means that whether your scans happen in native or whether they happen in Spark, your data is still going to be cached in your local cluster. And query optimization, as I said, we have invested and we've put a lot of work into coming up with great query optimization over the years. So all of the goodness of this proprietary query optimization from Fabric Spark is not lost when you enable the native engine, because it kind of kicks in only in the phase where you have this optimized plan that has gone through all of these rules that we have so carefully and lovingly developed over the years. So the native engine is a work in progress. It does not have feature parity with Spark. So this means that some operations can fall back depending on what you're using, but these fallbacks do happen seamlessly. Any operator or function which is not supported in native will fall back and be executed in Spark. So because the native engine is column-based and the Spark engine is row-based, when a fallback happens, you will see this transformation from columnar to row and then row to columnar again happening in your execution. So yeah, this can have, it could have a slight performance impact on your queries, but our expectation is that the overall speed up that you see should kind of mask any overhead that you would have due to fallbacks.
I have a little bit of a quick question around this one. So we've been talking about a single button press of enabling everything of the native execution engine on the entire environment. Is there any, and you may be getting there in the slides, I may be jumping ahead, I'm sorry, but I'm curious here. I was in another session with some other Microsoft team members talking about this. Can we enable the native execution engine on a notebook by notebook basis? And then
Yes.
let's imagine I'm going through a notebook and one of my commands it maybe falls back to something else. And maybe I want to not use a single cell. So again, we're thinking about, I'm kind of putting my business hat on here from the business team. I'm in this notebook, if everything's happy, but maybe I want to run this particular notebook with the native engine and there's one cell in the notebook that's not quite tuned or not ready for the native engine. Can we jump out of the native engine for a single cell and then jump back into it in a subsequent cell? You're nodding your head yes. I'm just confirming.
Yes. No, that is a great question. So yes,
Okay.
you can use one click, but we also have the ability for you to turn on and off the native engine anytime during execution of a notebook.
Awesome.
And this is using the Spark config spark.native.enable, which I think we do have documentation for. This is, I mean, it's actually a great scenario that you've talked about. So suppose you have a notebook which is running like 5 queries, maybe 4 queries are doing really great on the native engine. The 5th query, not so much, because a lot of things are falling back to Spark. You can just disable the native engine by running, that one Spark config set command in a cell before this query. And yeah, I mean, overall, like you're essentially leveraging the native engine to the best that it has to offer for the moment.
Excellent. I'm going to put the link in here just to be very clear here. I found the place inside the notes. So I'm going to put a link in the chat window. There'll be a link in the chat window of the Spark SQL, PySpark, Scala Spark, and the Spark R command. They're all of the commands will work in any of the languages. This is the command that you can use. It's a little documentation note here. So I'll put that in the window for the chat. If you want to control that down to the individual cell level, you have the ability to change the command directly in the notebook. So I just wanted to point that out. That's very cool. Something that I don't see happening other places. It's kind of like an all or nothing kind of scenario. That like the fact that you're giving us the ability to kind of really dial things in or out. So I just wanted to point that out. Excellent
Yeah.
point.
And the context is that, again, this functionality for the very first time we announced during the last build. It happened in May this year, right? So a few months ago, and it was based on the previous generation of the runtime. During the summer, we've been working on optimization and on supporting the newest Spark 3.5, so runtime 1.1, right? And again, that's why the announcement during the FabCon in Stockholm. But this feature is in preview. We are giving you ability to enable it, and you have a full control, enabling, disabling per each of the query as part of Spark setting, because it's still in preview. If you look in the, I know that we'll discuss the roadmap and more spicy questions, but if you look in the future, one day this feature maybe, and that's the future we are looking at, enabled by default. That will become, because why not? What's the purpose if we are not charging more for it? Why not to enable it? But yes, we follow Azure practices and all the requirements that we have to meet. So we are in a preview. There are a few months in preview. And once we proceed to the GA stage, for sure you will see more coverage of the operators. But the reality is right now we are still in the public preview of that functionality.
Yeah, good call out there. Still public preview. So, it's going to work for you, but just, this is for testing. Be cautious about running real production workloads and relying on things. That's why it's in preview. Excellent. I'll get out here and keep on going.
So dynamic memory management, which is something that I love talking to people about. So in Java, you have something called on-heap memory, which is essentially memory that's automatically managed by the GC. And in Spark, you control the amount of on-heap memory your process has through the config spark.executor.memory. So any memory that is out of the purview of this GC is what we call off-heap. And again, in Spark, you control this using spark.memory.offheap.size. So if you're like a hardcore Spark developer, you've maybe run into scenarios where you've had to tune these two configurations to make sure that some UDF or something that was not really running in Spark had enough memory to run and not run into out of memory issues. So if you had to sit and actually tune your on heap and your off heap memory, because in the case of the native engine, you may have some things that are executed in Spark which heavily relies on heap memory, and then Velox, which is written in C++ and needs memory that's not going to be randomly GC'd. If you have to sit and tune your individual workloads and say, okay, for this particular notebook, I'm going to have like a 50-50 split. And for this particular notebook, I'm going to have a 70-30 split. That's not a very fun experience. It does not fit into the whole goal and idea and motive of Fabric, which is to, take away all of these knobs and whistles from the user. So we at Microsoft developed this dynamic memory manager and have contributed this back to open source. So the dynamic memory manager sits behind the scenes. It kind of balances your allocation of on-heap and off-heap memory, and without you needing to specify upfront what the split needs to be. So it operates under the hood. It is a single memory manager for your Java and your C++ memory. And on the whole, it just offers better utilization of available memory, which means that you don't need to worry about your split upfront. And aligned with Spark's behavior, anytime the dynamic memory manager thinks that you're going to make a memory allocation that could lead to an out of memory error, it will simply fail your execution just as Spark would. So as part of the Spark history server, which you can navigate to on Fabric from your monitoring, we have a new tab, which is called the Gluten SQL tab, where you can look at how your query is being executed, look at the different fallbacks in your query, if there are any, and you can also see how your execution plan has been transformed, like what operators have been converted into native operators. And if you look at the SQL DAG, all of the operators that are executed natively are now highlighted in this Fabric green color to kind of make very explicit like what is being executed in native and what is not.
I believe it's particularly around those colors that you're seeing there. There are other engines in the marketplace that do a very similar thing. They do a very similar highlighting of colors, and so we're using the nice pretty green Fabric color here to let us know when the engine is picking up those new actions. So again, this really, me as a business user, I'm very overwhelmed by all the really cool things. Like it's neat, but there's a lot of code in here. And when you get into Spark, you'll see a lot of this. So it's just also helpful to learn these kind of things and just kind of know where to start looking for things. You'll get more comfortable with this over time. I don't expect
Yes.
anyone day one to get, oh, I really understand all the engine. I think the intent or purpose here is at a glance, you're getting some initial views of where the engine's taking over and where it's not. And then later on, as you get more advanced with this technique and these features, you'll know how further to dig in. And again, as you learn more, you'll be able to tune the cluster more, change things, figure out what engine's doing what. But again, this is a great lens as to what's occurring behind the scenes, which I think is a beautiful addition to the program.
Yeah. So at Microsoft, our team, we are very committed to contributing every feature or optimization that we come up with back to open source. So as of 3 weeks ago, we had about over 95 commits to Velox and over 176 commits to Gluten. That number may have gone up now. And we have contributed the dynamic memory manager, without which using the native engine would be a pain, because you would actually have to sit and tune your allocation of on-heap and off-heap memory for every single workload. We've contributed the Azure Storage Connector, which helps you read from Azure Storage accounts. We added support for timestamp data. We've contributed several performance optimizations in joins and scan, a couple of core Spark operators like the broadcast nested loop join and Cartesian product, a ton of Spark functions like various timestamp functions and string functions and other mathematical functions, a lot of bug fixes, and like that last bullet point, the list is honestly too long for this slide. But yeah, like I encourage everybody who watches this to go to GitHub, like explore commits, look at the stuff that we are contributing back to open source, and yeah, like we are super committed to just giving back to the community what it's giving to us. So let's understand execution. So we looked at like these various plans, which are kind of scary, but let's just break everything down. So if you have a very simple select sum, a simple aggregation query, this is how it's broken down into Spark. So this query would typically have two stages, which is a stage 0 and stage 1. And why it has two stages is because it's broken up by a shuffle, which kind of acts as what we call the stage boundary, meaning that at the end of that stage, data needs to be shuffled across these different executors before execution can pick up again. So if you look at the operators that are being executed to get you the results of this aggregation query, you start with a file scan on a Parquet file. And this then needs to be converted from columnar to row, because Spark is a row-based engine. So once this data is converted to row, just the particular column that you want, which in this case is price, is projected out. And we then do what we call a partial aggregate, because each executor just has its snapshot of the data. So each executor sums up whatever values of the price column it has assigned to it. And then this data is then shuffled to the driver, where a final aggregation is done to report the results back to the user. So if we go to the next slide, we can see how this plan looks like in the native engine. So again, we start with a file scan of a Parquet file, except in this case, it's a native file scan. So we no longer have the columnar to row stage, because the native engine is now a columnar engine. It no longer requires that data conversion. So we directly skip to project, where we get the particular column that we want. We go ahead with the partial sum. The data is then exchanged in columnar format to the driver, which then does its final aggregation, and the result is reported back to the user. So the very last operator that you see is Velox columnar to row. So this is simply because as humans, like we kind of expect our results to be in a row format. And if you see your results being returned to you in columnar format, it's not really going to make sense. So your final operator is typically going to be Velox columnar to row exec. And if you look at the words that are highlighted in yellow, so you see native, you see transformer, you see columnar, you see Velox. These are the key words that Gluten adds when it transforms the plan from what you saw in Spark to what you saw in native. So let's step through this one by one to see how it's actually transforming. So step one, you can see file scan getting converted to native file scan. And then step two, you can see columnar to row and project is replaced by a single project exec transformer, meaning it is a native project. Then step three, hash aggregate is then replaced by hash aggregate transformer. Step four, your exchange is then replaced with a columnar exchange. Step five, your shuffle query stage is then your shuffle remains the same because data needs to be shuffled, and then your final hash aggregate is replaced by hash aggregate transformer. And the little extra operator that you see, which is input iterator transformer, this is just something that Velox uses to allow Velox to read data that is shuffled. And lastly, your data is returned back to the user in the form of rows. So yeah, I mean, it's as simple as that.
I love this diagram. That is so clear as to what I'm looking at before. And again, one, I look at that stuff before, I'm like, okay, it's doing things. My numbers come out, the answer's there. Like, I'm great, happy with it. But the fact that we can now have a breakdown of what this, I mean, this makes total sense, right? I have potentially lots of files across many different machines. It's just trying to coordinate efforts between all the different machines and the workers. And so if you think about it from a very conceptual standpoint, it makes total sense. You're just running a bunch of code. You're organizing all the employees of my company to do different things, and they all have their little tasks. They get it done. They bring us back the results, and the results roll up. So in concept, it makes sense. But then seeing you so clearly educate us back down to like, these are what's happening and how it's transforming, that's really, really powerful here. And, initially you look at it going, oh my gosh, there's more steps. It's slower. No. They're done maybe more steps, but it's more efficiently. And I really like the idea that you made the analogy of, we're humans. We don't like to see things in columns. We like to see things in rows. And that's, the computers can be more efficient doing things in a columnar way. But for us, mere humans and mortals, we require a simpler format. And so that makes a lot of sense. That was really funny. I like that.
So the native engine is a work in progress, and we do have some limitations. So there are a bunch of delta operations that are not currently supported. So this includes merge, writes, deletion vector reads. Then we have Spark functions. So Spark 3.5 has about 436 built-in functions. And at the time of making these slides, approximately 326 of these are supported. But then these functions are in continuous development. We have a very active community that is constantly contributing support for more and more features into Velox and Gluten, both from Microsoft and also from the other open source community. Parquet and Delta are the supported file formats on the native engine. So if you do reads in JSON, CSV, which I know people still really love, and text, these will fall back to Spark. But we have this in the backlog, and we hope to support this in the future. ANSI SQL mode is also something that is unsupported. So if you turn your ANSI SQL mode on, all of your execution is going to fall back to Spark because Velox does not support ANSI SQL. And some complex data types like nested arrays with struct, these are currently not supported, but again, all in the backlog.
And the last aspect, which is, first of all, use the newest runtime. And this functionality is free for you. You need just to enable it, and there are no additional costs related with enabling. There are no additional costs related with using it. So it's free to use. As of now, it's still public preview, right? But after the FabCon, once we announce that we do not plan to charge for it, lots of people ask, okay, now because it's public preview, but then once it's GA, you will charge for it. And the answer is we do not have any plans for that. We plan to keep it free for you so you can get the benefit of faster execution just by enabling that without any additional cost.
I can't stress how important this is for us, the community here. I think there's been a lot of internal conversations between Microsoft and customers, and I'm sure this was a very heated discussion internally. Again, not knowing the inner politics of what's going on here, but I'm very pleased that we landed on this, and I think this is going to be a great moment for us, just from a capability, a feature standpoint, and again, at the end of the day, we're just trying to get data through the system. I need to get data in out of these systems. I need to get it stored somewhere. I need to get it into my reports. And the faster I can get there at less cost is just a bigger win for us all around. So I love the fact you're doing this.
Yeah, we were in a stage of private preview for that functionality for a long time with lots of MVPs, with lots of customers. We listened to your feedback, and the feedback was clear. And that's why it's free to use.
Thank
and
you.
what I want to emphasize that, again, Native Execution Engine is based on two open source components. At the same time, our big team have been working on that on multiple improvements, and we contributed back to the community. We are part of the community for those projects, Velox and for Gluten. But even what I want to stress even more is our collaboration with our great partners like Meta, like Intel, like IBM. So we are a group of big companies which are aiming to do the big data processing, and together, because of those two beautiful components, two big hearts, Velox and Gluten, we could make that functionality happening for you again. One more time, just as of now as a checkbox. In the future, it will be fully embedded. Of course, you always will get the possibility to enable, disable, but as of now, it's just a simple single checkbox.
Awesome. I think this is our last slide. With that, I'll say we'll take off the slides here. I just want to say thank you very much for our presenters today. Amazing presentation. I am floored. The slides are so clear. These are some of the best articulated examples of how the engine's working, what's happening under the hood. So I really want to say thank you so much for such a clear presentation about what's going on here. The community loves this kind of stuff. We're going to continue to push this feature hard. We think everyone should learn it. We think this is like a no-brainer. All of my clients, I'm pushing to use notebooks and get more into it. This is the future of what we're going to do for data and analytics. So thank you so much, team. A lot of people complain about features that are not right. They don't have things. They're not there. I just want to say from the bottom of our heart in the community, we really appreciate all the hard work and how well you've been listening to the community and providing things that just rock. I mean, honestly, I'm just thrilled and excited and very happy to talk about this feature. So Ankita and Estera, thank you so much for presenting today. We had a wonderful time, and we should talk about doing some more things in the future. So tee up some other great slides from us. We'd love to go deep on the Spark engine, the native engine, any new features you're coming out with. We'd love to have you back on and just do some more of this. So with that, I'll say thank you so much. And everyone,